This is the video 7-5 parametric equations, and the first thing on here is the objective for parametric equations. This is an introduction, so I want you to know what a parametric equation is, be able to graph a parametric equation, go back and forth between a rectangular equation or parametric. Also be able to graph a conic section. I'm going to teach you how to graph an ellipse using a parametric equation and solve some of the problems that we solved with vectors with parametrics. So to describe what a parametric equation is, so far this year all we've done is we've graphed in an xy plane. So we've had an x value and a y value, and we've just had one equation involving the variables x and y. In this lesson we're going to represent some of these same equations using two variables, using two equations, x and y, an equation for x and an equation for y, using a third variable, and that third variable that we're going to use is t. So we're going to have an equation with x in terms of t and y in terms of t. So explain why, or how valuable parametrics, if I go back to what we studied with vectors and I describe a problem that we've studied before with vectors. We have an airplane is flying due north at 250 miles per hour. So if I drew a vector to represent that, I would have 250 miles per hour flying due north. And it also says that the wind is blowing east 50 miles per hour. So I'd want to set up the vector for the wind starting at the tip of the other vector. So I would start this vector 50 miles per hour. And then here is my resultant vector. So if I try to write an equation to represent this situation, I would have, I could graph the vertical distance that the plane has traveled versus the time that has passed, and that would be right here. So this is my x-axis with time, and at 1 hour we could see that the plane has traveled. Each of this scale here is counting by 50, so that's 100, 200, 300. You could see that at 1 hour the plane has traveled 250 miles because it's traveling 250 miles per hour. But we can't see direction. We just know at 1 hour it's gone 250 miles north. We could also have a graph y equals 50 times x, and we can see because of the wind in 1 hour that the plane, same scale here, would have been blown 50 miles to the east. What a parametric equation would allow us to do is write an equation for x. X would be the horizontal distance, so x would equal 50 times t, and an equation for y, where y is the vertical distance. And then we can see here that the same points that we have represented in the other graph, at 1 hour the plane would be 50 miles east and 250 miles north. And so this graph, it shows the orientation, and it's a little more like the vector. And so this is a parametric equation where you have an equation for x and you have an equation for y. The third graph would allow us to determine the position of the plane at any time, and the variable t is called a parameter, and the parameter in this case is time. So first, how you work with a parametric equation. I'm going to do an example to show you how to graph one. So it says sketch the curve if x is equal to t squared plus 5 and y is equal to t divided by 2 plus 4. And in order to sketch this equation over a given interval, you must make a table to find both the x and y values, and then you're going to plot the x and y values. So t allows you to calculate x and y, but you're going to be plotting x and y. So x is t squared plus 5, negative 4 squared plus 5 is 16, plus 5 is 21, 9 squared, or negative 3 squared is 9, plus 5 is 14, negative 2 squared is 4, plus 5 is 9, negative 1 squared is 1, plus 5 is 6, 0 squared is 5, 0 squared is 0, plus 5 is 5. And then this pattern is going to repeat. and that was using the equation for x. Now using the equation for y, I'm going to take half of my t value and add 4. So half of negative 4 is negative 2, plus 4 is 2. Half of negative 3 is negative 1.5, plus 4. It's like subtracting 1.5 from 4, so 2.5. Half of negative 2 is negative 1, plus 4 is 3. Half of negative 1 is negative a half, plus 4 is 3.5. I'm starting to see a pattern here. Half of 0 is 0, plus 4. You can see the pattern 2, 2.5, 3, 3.5, 4, 4.5, 5.5, 6, and 6.5. So this, I'm graphing this over the interval from negative 4 to 4. And one of the other value of parametric equations, you can start and stop parametric equations wherever you would like. So this is actually going to start when t is negative 4 at the point negative 21, 2 when t is equal to negative 4. And it's actually a starting point. And then graphing the next point. Notice I'm not graphing t is negative 4. I'm just going over 21 in the x direction and up 2. Over 21 up 2. I'm just marking it with the t is negative 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just to give me a scale here so I don't have to count every single time. 11, 12, 13, 14, 15. So when x is 14, y is 2.5. When x is 9, y is 3. X is 6, y is 3.5. 5 is 4, and then this pattern starts to repeat again. So here, I'm going to connect this with a nice smooth curve. When you're doing parametric equations on your calculator, you get to dictate how many points the calculator uses to make the graph. And so right here my t-scale is 1, and I'm able to make a nice smooth curve, but my calculator would actually connect those with straight lines. So if you are graphing on your calculator, instead of making your t-step 1, you would want to make it 0.1 so that you would get enough of a curve, because the calculator would connect this with a straight line and it might look like a V. So t is negative 4 here, t is equal to negative 3, t is equal to negative 2, t is equal to 0. So this particular graph is going in this direction, and it stops when t is equal to 4. So just to summarize, to graph a parametric equation, substitute t into both equations for x and y, find those values, and plot the values. On the next page, this is just how do we work with parametrics, how do we write parametric equations, and then some of the things we can do with parametric. So to change a regular rectangular equation, or just, a regular, they call it in the book a rectangular equation, the f of x notation that we're used to. And I'm going to change this. On your notes it will be changed. I'm going to change this to 2x squared minus 4x plus 3, just so it will show up on the graph easier. Should be already changed on your notes. If you're going to change a regular equation into parametric, you want to have an equation for x and you want to have an equation for y. A simple way to do this is if you let x equal t, then what you need to do to find the y equation is just let the y value equal the function, but instead of having x's, we need to use the other parameter. We need to use t. And what this does is it works exactly like this function. If I plug 1 in, I would get a y value. So if I plug 1 in for t, if x was equal to 1, t would be equal to 1. So easy way to change regular equations into parametric. Just set your x equal to t and y equal to the function with respect to t instead of x. This is really easy then. One of the advantages of parametrics is you can graph things that are not functions. And so one of the things we've done earlier this year is we've looked at this graph and we've decided whether the inverse would be a function. Well, we know this is a parabola, it's a quadratic, and a parabola does not pass the horizontal line test. And because it doesn't pass the horizontal line test, that means that the inverse relation of this function would not be a function. And I can find that and show that real easy with parametrics. So we had our original equation, f of x was equal to 2x squared minus 4x plus 3. And that original equation in parametric, written as a parametric equation, would be x equals t and y equals 2t squared minus 4t plus 3, just what I've done up above. If I want to find the inverse, well, when we find inverse, we switch x and y. Well, the nice thing with parametric is I can switch x and y equations, and that will switch my x coordinate and my y coordinate. So if I let the x equation equal the function, and the y equation equal t, that will graph the inverse relation. So let's graph this on our calculator instead of plotting points like we did last time. I'm going to use the Inspire. If you do have an 84, the only difference with the 84, so I'll just go through the 84 real quick, is you can graph parametric just the same. First thing you need to do is hit your mode button and change it to parametric mode right here. And then anytime we're changing the window, that shows up in the equation tab on the Inspires, you're going to need to change your window by pressing the window button. So the T-min and the T-max, you're going to press the window button. One other thing to note in the 84s, when you press the variable button, the x, t, theta, n, notice that it will just type t's for you. Do not use x's, and that's true for both calculators. So if you have an 84, you should be able to follow along. So on the Inspires, you want to dock B your calculator and go to your scratch pad, and we want to enter in this equation. If we don't change the graph type, it's going to be a regular rectangular equation. So the first thing you want to do is, just like when we graphed conics, you want to hit Menu, and you want to go to number 3, Graph Entry. And unlike when we did conics, we chose conics, we want to choose parametric, which on my calculator is number 3, but I think I might have an old operating system. So choose parametric. Let's graph the original. So you want to put x is equal to t. And for your y value, we picked 2t squared. Sorry, I hit the cursor and it went to the wrong spot. Minus 4t plus 3. And if I graph that, let me move the equation here. Notice that it only started the parabola when x was equal to 0. And because x is equal to t, that's saying when t is equal to 0. So if I want to see the whole entire equation, go back to your, press tab again, or if you have an 84, go to your window. These numbers right down here, it says 0 to 6.28 or 0 to 2 pi. If t is starting at 0, so if I want to see the whole equation, I want to change that so my t values are not starting at 0, they're starting, let's say, negative 10. Because that's what my window is. My x values are going from negative 10 to 10. So I would want my t values, I'll change the t max here also. I would want my t values to go from negative 10 to 10. A good default t-step is always 0.1. The calculator has 0.3, but I'm going to change it to 0.1. And that should make a nice graph. And notice now it has the whole complete parabola. Just another demonstration so you can see, if you make your t-step too big, let's change our t-step to 2, it's not going to plot enough points, and this nice smooth curve, nice parabola that I have, is going to get jagged. No, it's okay. It's hard to see. Maybe you can see it on your own calculator. This is straight and not curved like it was before. So I'll stop playing and change that back to 0.1. So T max is -10. T min is -10. T max is 10. And my T step I'm going to leave at 0.1. Now to graph the inverse. Now we know the inverse, the graph should be reflected over the line y equals x. I want to type in the equation and I want to switch my x and y values. So my x value is now going to be 2t squared minus 4t plus 3, and my y equation is going to be t. And again, I want to make this t min -10 so I get a complete graph here. And I'm going to change my t-step to 0.1 because that's what I saw was used for a default. And there I can see that I was able to graph the inverse with one parametric equation, and that it is a reflection over that line y equals x, and that is the inverse relation for my parabola. So if you want to, I'm going to sketch those real quick on my notes. So here was the original, and this is just a sketch, and here is that same graph, the inverse of my original graph. So another advantage of parametric equations is you can find an inverse equation really easily, whereas if I was going to find an inverse equation in rectangular mode, I'd have to switch x and y and solve for y, which would be difficult here because it is a quadratic, and it's easier in parametric. And it allows me to graph things that are not functions as one equation. Example 3, in example 2 we learned how to write a rectangular in parametric. Example 3 is how do we take a parametric and write it in regular function notation or rectangular form. And what you want to do is you need to do some substitution. You need to substitute t into the y equation. So the first step is you want to solve for t. So I have the equation x equals -3 times t. I'm going to divide both sides by -3 and find out that t is equal to x divided by -3. Second, I want to substitute this value, x divided by -3, into my y equation. So instead of having y equals t squared, I'm going to have y equals x divided by -3 squared plus 2. And now I have a parametric equation in rectangular form or regular function notation. This next page is how do we graph conics, and my didn't print off right here. Graph the relation below in parametric mode and sketch the result. So this time what I want to graph is a conic section, and you know from the unit circle that if I let x equal cosine and y equal sine, that will make a circle. So I'm going to let x equals, I'm going to put 3 plus cosine, just so we can see what happens if I add a number to cosine. If I just did x equals cosine, we'd just get the unit circle with a center at 0, 0 and a radius of 1. And y equals sine, I'm going to multiply the sine by a number so we can see what happens when we multiply by sine. T min, t is my angle, and I'm going to be taking the sine of that angle. So if I go from 0 to 2 pi, that will go around the circle, and again a t-step of 0.1 is enough to make a nice smooth curve. So we know this would be a circle, but this 5 is going to actually stretch it in the y direction, and the 3 is going to slide it over in the x direction. So instead of being a unit circle with the center at 0, 0, this is going to have the center at 3, 0 because it's been moved 3 spaces over. And instead of having a radius of 1, it will have a radius of 1 in the x direction. But instead of having a radius of 1 in the y direction, the radius is going to be 5. So this will make an ellipse. And if you add a number to the x-coordinate, it will move it right or left. And if you multiply a number by the cosine, which is in the x-coordinate, it would change that radius from 1 to another number. And since I made this number the 5 times sine, that made the radius in the y direction 5. So the general equations here, x is going to equal h plus, and I'm gonna call the radius in the x direction a, cosine of t, and y is going to equal k plus b times the sine of t. And so if you want to graph an ellipse with a center of h and k, you would put the h value in the x equation and the k value in the y equation. And if you want to change the radius, like here I have a is equal to 1, so the radius is 1, and b is equal to 5, so the radius is 5. And I can graph that on the calculator to show you. Clear my calculator. When you do this, make sure you check your settings. It's really important that if you're going from 0 to 2 pi, your document settings need to be in radians. So I hit the dock button and I'm going to change those to radians. And go back to the graphing calculator and menu and change it to the graph type to parametric. So if I put 3 plus the cosine of t times 5 times the sine of t, and this is already set to go from 0 to 2 pi with the t-step of 0.3, so that's 0.13, and there it makes a nice ellipse. Playing with this just a little bit, let's change, let's put a plus 2 here, and that's making the k value 2, so it will move that ellipse up. Or if I want to stretch it, if I want to stretch it in the x direction, cosine is x, so let's stretch it way out here and put a 10. I'll stretch that ellipse out, so now the radius from the center is 3, 2, because I added 2 to the y equation. The radius in the x direction would be 10 because I put a 10 in front of the cosine. So you can graph an ellipse or a circle using x equals cosine and y equals sine. If you want to play around, you can actually graph hyperbolas. You just need to let x equals secant and y equal tangent, and it's the same properties. Now, if we want to change this equation, or actually let me use my more complicated equation that I have here with the center at 3, 2 and a horizontal radius of 10 and a vertical radius of 5. Let's change that into rectangular mode, and which we had worked with in chapter 7. So, and to do that we can use the Pythagorean property for sine and cosine that we learned in chapter 5, and we can rewrite the parametric equation as a rectangular function that involves x and y. So the steps to do that, the parametric equation, we know that the cosine squared of t plus sine squared of t, that's that Pythagorean theorem identity that we memorized, is equal to 1. We memorized that in chapter 4. So if we have an equation for x, and the equation I had was 3 plus 10 times the cosine of t, and we have an equation for y, I think I had 2 plus 5 times the sine of t. If we want to solve that and eliminate the parameter of t, the first step is we want to solve for cosine. So solve for cosine of t and sine of t. So we just want to rewrite those equations so that they say cosine of t and sine of t. So here, I'm a little short on space. So if I want to get cosine all by itself, I want to isolate the cosine. I would subtract the 3 over to the other side, and that would make this x minus 3 equals 10 times the cosine of t. But I want cosine isolated, so then I would divide by 10. So I have cosine of t equals x minus 3 divided by 10. Doing the same thing for sine, I could subtract the 2, get y minus 2 equals 5 times the sine of t, and divide by 5, so that the sine of t is equal to y minus 2 divided by 5. Now my second step, then, after I have done this, would be substitute my two equations into the Pythagorean theorem equation, cosine squared plus sine squared equals 1. So substitute cosine of t and replace that with x minus 3 divided by 10. And replace sine of t with y minus 2 divided by 5. So instead of having cosine squared, I'm going to write x minus 3 divided by 10 squared plus sine squared, but I'm not going to write sine squared, I'm going to write y minus 2 over 5 squared equals 1. And we know from chapter 7 this is an ellipse with a center at 3, 2 and a radius in the horizontal direction of 10 and a radius in the vertical direction of 5. Which is what we have here on the calculator in parametric. So that's how to change parametric into rectangular for conics. Sorry, on the last one I didn't have the last page here. So here's the last example. Kaylee is practicing free throws for an upcoming basketball game. She releases the ball with an initial velocity of 24 feet per second at an angle of 53 degrees. And so you can see here they show like a vector, and we've been working with vectors. So if I draw a vector that 24 feet per second and the 53 degrees, we would want to use the vertical and horizontal components here, because the question they're asking is, does she make the free throw? And so this would tell us the horizontal. We're going to break this situation into a horizontal equation and a vertical equation. And so we're going to use parametric equations and have one equation for x, which will represent our horizontal distance traveled by the ball, and one for y, which will be the vertical distance. So the other information that they give us, the horizontal distance from the free throw line to the front of the rim is 13 feet, and the vertical distance from the floor to the rim is 10 feet. The front of the rim is 2 feet from the backboard, and she releases the shot 4.75 feet from the ground, because that's how tall she is, or where her arms, where she releases the shot. And the question is, does she make the basket? Well, we know the ball. Well, first we have to find the horizontal component, which if we use cosine of 53 degrees, looking at this right triangle here, the cosine of 53 degrees is equal to adjacent over hypotenuse, which is x over 24. So we know x is equal to the cosine of 53 degrees times 24. Setting up the same equation for sine, we can find that the vertical component would be sine equals 53 degrees times 24. Since that's a velocity, I'll move that over there. Since that's a velocity that the ball is traveling in the horizontal direction, we can figure out how far the ball travels by multiplying this by the time that the ball's in the air. So the equation for the x value would be, I'm going to move the 24 in front, cosine times 24 times the cosine of 53 times t, and that would represent the horizontal movement of the ball. In the vertical direction, she throws the ball from 7.5 feet, so we need to add that to the 24 sine of 53 degrees times t. And then also in the vertical direction you have gravity, and gravity then is going to make the ball go down, so we want to subtract negative 16t squared, and that's a constant for it's going to be negative 16t squared every time if it's feet per second and negative 9.8 if it's in meters per second. So the question is if she's going to make the basket. So the first thing what we need to figure out is how long would it take the ball to travel this 13 feet? So if I let x equal 13, I can figure out what t would equal when x is equal to 13. So t would equal 13 divided by 24 times the cosine of 53. So I want to make sure that my calculator is in degrees, and I just want to do 13 divided by the whole quantity of 24 times the cosine of 53. And that 0.900 means that it will take, when t is approximately 0.9 seconds, that ball is going to travel that 13 feet. So now if I plug that into the vertical equation, I don't know if I need to write this all again. If I plug in 0.9 into the vertical equation, then I can see does the ball go high enough. It needs to be 10 feet in the air at 0.9 seconds in order for her to make the basket. So plugging this all in, since I have it here, I can use my answer. I can go 4.75 plus 24 times the sine of 53 degrees times my last answer minus 16 times that answer squared. And I find out that the vertical distance the ball would travel would be 9.04 feet. Because the basket is 10 feet high, if we look back up here at the picture, she would be at 9 seconds, she would be here, and so that flight of the ball, she would be below the rim and she would not make the basket. So we want to check our work here, and we can check it with the calculator. So far we figured out that it would take 0.9 seconds for the ball to travel the 13 feet in the horizontal distance, and after 0.9 seconds the ball would be at 0.9 feet, which is below the 10-foot basket, so she wouldn't make that. And then we would like to check that on the calculator. So first thing you want to do is you want to make sure that your calculator is in parametric mode. So I pressed menu and then option number 3, which is graph entry, change to parametric mode. I want to enter the equations in here. So my first equation for the horizontal distance is 24 times the cosine of 53 degrees times t, and for vertical 4.75 plus 24 times the sine, oops, that was inverse sine, times the sine of 53 degrees times t minus 16 times t squared. My Tmin and Tmax is the time that the ball's in the air. So we know that the ball at 0.9 seconds has traveled the 13 feet. So I really don't need to go much over 1 second. So let's go 1.5 seconds. And again, I'm going to use the default t-step of 0.1. So if I graph this, here I've set my calculator in degrees, but I had to play with that a little bit. If you press dock, it will change the table and the scratch pad, but it won't change the graphing angle. So if your graph doesn't look like this to start, press menu and go to settings number 8. Press menu 8 for settings and make sure your graphing angle is in degrees. I had to change that on my calculator to make this work. And mine is, so I'm just going to escape, but for yours you would go make default. We know the basket's 10 feet high, so my Y max has to be bigger than 10 feet. Actually, I'm going to go menu and change my whole window here. So X, I don't need any negative X direction, and it's traveling 13 feet, so let's go 15. And y min can be 0 and y max, let's go 15. So here's the flight of the ball. One of the nice things I can do is I can add a second parametric equation to represent the hoop. So if I do that, I want the x-coordinate to stay at the 13 feet because that's where the hoop is, and I would like the y-coordinate to change. So let's say we want that to be t, because that's my variable, and we want t to go in between 0 feet and 10 feet. So I can also get my calculator there to graph the hoop. And now you can see as the ball travels, the ball is going to be below the basketball hoop at 0.9 seconds, and so she will not make the basket. Last thing, I can trace along here to show you that. And we can see here it shows us like the time, the horizontal distance, and the vertical distance. So if we trace along, we can see that, oops, went a little fast there. We can see that like at 0.8 seconds, the ball is already below the hoop because the vertical distance is 9.8. So we can see that her shot is going to be too low here. And then this point at 0.98 seconds, it's gone past the hoop, which is at 13, a horizontal distance of 13. But again, this just shows that she will not make the basket. If you try this on your 84, put the same equations in there that we did. You can pause that if you need to. Set your window. And the hard thing about the 84 is you can't set a different t step and t max. So it will graph really slowly. But the very first time, the nice thing about the 84 is if you change your graph type right here to what looks like a basketball, the very first time you graph it, it will look actually like a basketball flying through the air. But the basketball hoop takes a lot longer to be drawn, so you can't see the hoop for quite a while. So just to show you that you can do this on the 84 also.